So this is our complete optical or light wave system. So in the system, we have 5 components: 1, 2, 3, 4, 5: laser, modulator, fiber, amplifier, and detector. Each one individually, before mid and after mid, in combined, we have studied various characteristics, all the fundamental components. If you combine them, you can have a complete system diagram. Of course, your system may vary depending on the what kind of system you want, right? Okay, so I will show you today what we will do. I will show you a practical system, practical light wave system. We'll try to find what kind of components are there. Probably they will check out our these components, and then in the system how they works. Probably we will solve some equations also. Okay, so let's see a system diagram. This is a system diagram. Let me zoom in. This is a complete system diagram of any. This is a typical one. Okay. Okay. So here we use a extreme use of optics in a very advanced technology, right? So here there is an antenna here. So okay, we have this slide also here. This one. This is the one I am talking about. This is the system diagram. So this is a complete. This is a how to. Okay, this is a antenna. This is actually in the RF domain. RF domain. This portion is totally in the optical domain. So this is optical domain. The fundamental application of optics actually is to replace the conventional RF system. That is actually the main applicational advantage in optics. So that is actually happening here. Okay, I will actually explain you the stage by stage. Okay, so what is happening here? This is a typical receiver system. Let's talk a typical receiver system in RF domain. RF domain. Let's see a RF system, how we can convert the whole RF system to the optical system by using these components. Okay, so this is actually a typical. This is actually this one a typical dish antenna, parabolic antenna. We may use it for our dish TV. Okay, guys, are you following?
Yes, sir.
Okay, so I will give you an example of a typical RF system, what you easily understand or what you usually know from our daily life, and we can see how totally system can be replaced by an optical system. That will be more understandable. So this is actually our parabolic or dish antenna, dish TV. What happens on the satellite? You receive a signal, dish antenna signal. Okay, typically our satellite signal is in Ku band. Ku band. Ku band is around 10 gigahertz signal. Okay, that signal you are receiving. Okay, so in dish antenna, this is a typical. This is not exactly the dish antenna. We called it phased array antenna, but still it's RF signal. Phased array antenna, which is also a typical RF system. Instead of like it's a dish size, it's actually flat size. There are small antennas, lots of small antennas here actually. You know the patch antenna, right? So this is actually small patch antennas here, and that actually here this is the zoomed in version. You see, this only one tile actually is zoomed in here, so that there is actually 8 into 8 array. So how many here is probably 22. So 8 into 8 into 22. So how many arrays is there? That is not a big deal. So 10 gigahertz signal However, the 10 gigahertz signal actually received here. Still here you see RF 10 gigahertz, 10 gigahertz signal. Okay, this is an LNA that is also in the part of the this dish antenna. LNA means what? LNA is low noise amplifier. Low noise amplifier. Okay, so means this signal will be very weak signal because it's coming from the thousands of kilometer away from the satellite. So that signal, very weak signal, will be amplified here, still in RF domain. Then the signal will be mixed here. This is a mixture. You see, this is an arrow. This is a mixture by this LO. What is this LO? LO is called local oscillator. This is nothing but an oscillator. Oscillator means it has a frequency and it's locally produced. That's why it's called local oscillator. So what this local oscillator frequency is? Imagine this local oscillator frequency is 9.5 gigahertz. This 9.5 gigahertz signal is mixing with the 10 gigahertz signal, isn't it? So in this mixture, if I draw it separately, this is a 10 gigahertz signal, 10 gigahertz signal, and from our local oscillator or LO, I'm generating 9.5 gigahertz. What will be the output from this mixture? For example, this is F1, this is F2, F2. What is the output of this mixture? F1 plus F2 and F1 minus F2, isn't it? You know it from your RF courses. So you see F1 plus F2 means what? It's 10 plus 9.5 is almost 19 gigahertz. 19 gigahertz is very high, 19.5 gigahertz. And F1 minus F2 will be only 0.5 gigahertz. So when you find that signal, we call it IF, intermediate frequency. Intermediate means this frequency is yet to be, it will go for next further processing. That's why it's called intermediate frequency. Okay, so here probably this signal will be amplified, blah blah blah, lots of process will be doing, and this high frequency 19.5 gigahertz, that will be automatically discarded in the system, because the system do not have that much bandwidth, but the system will consider 0.5. That's the signal. Actually this IF signal actually goes to the set top box. Set top box. Whenever you use a dish antenna in your house, there is a set top box, right, where you control the channel, everything. Means actually this 0.5 gigahertz, it comes here. 0.5 gigahertz comes here, and then you do this processing. You change the channel or you amplify. All these things happens in the, you see everything is still in the RF, right? Here let me highlight. Is it RF? Yes, it's RF. Is it RF? It's RF. IF signal is still in RF. In set top box, this is still in RF. It's all about RF signal. Got it, guys? This is a typical RF system. So what we are intending to apply some of the mechanism of optics in this RF system. Got it, guys? How this RF system works? I will summarize here. So you receive a antenna, dish antenna, which is actually like satellite signal, 10 gigahertz. This 10 gigahertz signal, probably their amplified little bit in LNA. Then you pass it through a mixture where you have a LO, local oscillator, and you have the IF signal, intermediate frequency. If this LO is 9.5 gigahertz, then in IF you will have 0.5 or 500 megahertz, 0.5 gigahertz, this signal. This is very low frequency, which will be goes to the set top box so that you can process it further. So this was an RF signal, RF. Here is also RF. Here is also RF. Is also RF here. Understand, guys, this one? Up to this is okay, right? It's RF signal. Okay.
Yes, sir.
Let's see how we can implement our optics here. Okay, now see, this is okay. Let us first show you the extreme example of this kind of RF system. I say extreme example of this kind of RF system. Let's see, it's actually practically implemented or not. So still, it's using in many systems, huh? Practically, it's implemented. Okay, see this figure. Okay, see this figure. This is a one of extreme application of how RF can be converted to an optics. Okay, here I took an example of ALMA. ALMA. What is ALMA? ALMA is nothing but Atacama Large Millimeter Array. Atacama Large Millimeter Array. Okay, array we know is a range of antennas. Millimeter because this is in the millimeter range. Millimeter means what? 10 to the power minus milli, 3 meter millimeter array. So what is the frequency? This is the wavelength, lambda millimeter. If this is the lambda, what will be the frequency? F frequency will be c by lambda. What is c? C is nothing but 3 into 10 to the power 8, and lambda is 10 to the minus 3. So it will be 10 to the power plus 3, right? If I took it there, so it will be 3 into 10 to the power 11. You see, it's actually in terahertz. Terahertz is 10 to the power 12. How is very high frequency. That's why it's called millimeter. Very, very high frequency. Okay. What is this Atacama? Atacama is the name comes from the desert. This is the this happens in the Chile here. This is the country called Chile. There is a location, probably somewhere here. There is a desert, and there they install this large. You see these big dish antennas. Dish antennas. You see they're very, very large, and these dish antennas are synchronized. What they do, they actually tries to focus on the sky to receive very weak RF signal, radio frequency coming from the extraterrestrial element. From that element, what happens when they are synchronized? This kind of picture is produced. You see, what is this? Are you familiar with this picture? This kind of picture. This is actually the picture from galaxies, outer galaxies, based on the radio signal. Okay, so here see this system, this one is totally an RF system. This one, this whole system can be converted to an optical system by using this system. You see, these are the dish antennas. These are the dish antennas. Lots of antennas. They will receive the signal. This system can be replaced by this one. You see, these are antennas, small antennas. We call it phased array antenna. This is not the scope of our lecture today. What is a phased array antenna? Right? Phased array antenna is nothing but where you have small like antenna element, small element. They will combine together so that they can work as a normal antenna. That's actually nothing but a phased antenna. Means phased antenna. You see, this antenna had to move from one place to another, or the direction, this direction or that direction. But this phased antenna do not have to move. That is not part of our lecture. Okay, like this course. So what happen is, if we can use this phased array antenna, then what? We can, this phased array antenna, you see, this phased array antenna will be replaced to our this system, the one we are talking about. This one. This one. Imagine this is only one of the element of the phased array antenna. What happened then? This is the LNA, then you have RF, you have LO and IF. What we'll do then, we will actually replace this LO, local oscillator, by using, probably previously it was RF. Now you will use an optics to create this LO. optics. That will actually here in this system. You see here there are lots of yellow line here. All the yellow go to the central office. For example, imagine here is a central office. From the central office, you can distribute this yellow here. So the complete system can be part of the system. You can replace by is optical equivalent optical domain. Okay, so this is actually an extreme example that okay, if you have a complete RF system, you can replace some of the components so that it can be an optical system. Following the same thing, I'm giving you still, we are still in the example. This is the system. You see here, we go to the here. Okay, you see this is RF, right? Where you use from a phase array antenna, you receive the RF signal, RF signal. Okay, okay. RF goes to LNS. Is it RF or what happens? Low noise amplifier. Is it still in RF? You received an RF signal like satellite signal or whatever, any RF signal, and you amplify the signal. Is it still in RF? Guys? Still in RF, right?
Yes, sir. It's still in RF, sir.
RF. So then it goes to a mixture. Is it still in RF? It's still in RF because in mixture there we use another local oscillator. You see that was the local oscillator RF. That local oscillator we completely replace by an optical system. Then means what? The signal that is coming out, we will convert this RF to optics. RF to optics. Optics. That's why it's called electrical signal to optical signal. How? Which device converts electrical to optical signal? Remember which device do that? Electrical signal to the optical signal? Mixture, right? Mach Zehnder modulator. What Mach Zehnder modulator do? We show you in our system diagram. Mach Zehnder modulator, this one. This is our optical signal, RF signal. Means RF signal is inserted in the optical signal. So this optical signal in the output of the Mach Zehnder modulator, which is actually optical, but the RF signal is inserted there, right? Same thing. Same thing. You see, mixture RF signal we convert it to the optical signal by using mixture. Then all the signal goes to a photonics beamformer. Because actually this is not part of your study, because when the signal was received in the each antenna element, there was a little difference in the phase that will be corrected here. That is not your our scope. Then all these optical things doing, and the receiver means photodetector. You see, we convert optical signal to the electrical signal again, and we do it receiver. Means actually the whole RF system which we did it previously, we say here we have a scope of using an optical signal, and here we have a scope of optical signal that we can be converted and processing. You see, this is the processor, optical processor. This processor will be like quite complex if you use an RF signal. That's why we convert it to the optical signal. That's I'm trying to say. Means from here we can summary that okay, what is the application of optical signal? We have two application of this like photonics in general. How many application? We have two application. Application one is so optical generation. So optical generation, and application 2 is optical transmission. This is in broader sense. There are two ways you can use an optical system by using optical like carrier generation. We can say it. You see this yellow Local oscillator, it was previously RF. We want to convert it to optics. So it is called optical carrier generation. LO comes from the local oscillator, from the RF domain. When we go to the optical domain, we usually do not call it LO, local oscillator. We call it carrier. It's still LO, local oscillator signal. So we can generate an optical LO, or we can transmit an optical LO. When we need an optical LO transmission, in so give me let me give you example 2 first. So optical transmission. Give me an example of optical transmission. Why do we need that? Why do we need an optical transmission? In telecommunication, right? In telecom, what do we do in telecom? You have all the RF signal. You have lots of RF signal, right? All signals are RF. That signal must have to go through an Mach Zehnder modulator, MZM. Or if I can draw it reversely, other way, let me draw it other way. So you have lots of RF signal, many RF signal for hundreds of thousands of users. RF, individual user. So you will pass it through the Mach Zehnder modulator. Oh, sorry, this is RF. We will pass it through the Mach Zehnder modulator. What Mach Zehnder modulator do? Mach Zehnder modulator take a laser signal 1, laser signal 2, laser signal 3, and then convert it to the optical domain. So this RF will be in the this RF signal, which is actually like this one, this way, RF signal, this RF signal, this RF signal. They are actually now inserted in the optical signal. They are inserted in the optical signal. Means optical signal was modulated according to this RF. It was a light signal, right? Now light is actually, so here the what is the frequency? 10 to the power 12. RF signal was a few gigahertz, like 1 gigahertz, for example. 1 gigahertz. 1 gigahertz. Now this 1 gigahertz is where? In this 12. 10 to the power 12. 10 to the power 12 is now here in 10 to the power 12. 10 to the power 12. So this 1 gigahertz is now inserted in the 10 to the power 12. This 1 gigahertz signal is now inserted in the terahertz signal. Right? Then lots of signals. So they probably what you can do, you can combine them in WDM, wavelength division multiplexer. Then you can transmit it through optical fiber along like thousands of kilometers. Then in the receiver or other operation, DWDM, which will be demodulation, DWDM, like DWDM. You modulate it, all the signal, and you demodulate it. Then typically all this reverse process happens. So the small RF signal you are actually transmitting through an optical so that you can process it. There is one. So what is the benefit of this one? So you have 1 gigahertz RF signal and you have 10 to the 12 hertz, terahertz, which is optical signal. What is the difference between the two? Of course, it's high frequency. What is the benefit of going to this high frequency? Immunity of interference. If when you are in the in this range gigahertz, you have lots of surrounding sources. For example, other mobile communication, other mobile lightning strike, thundering, or everything actually creates interference to this signal. But hardly there are any signal, communication signal at this frequency. But because this is not a microwave, so there is, so in optical signal is immune for interference and EMI, electromagnetic interference, which usually comes from the nature, this electromagnetic interference or other electromagnetic devices. So optics is very much isolated from there. Means actually you have very good processing mechanism. You need very less complex mechanism. That's actually a optical transmission system, typical optical transmission system. Okay, this system can be very complex, like from ranging from very simple to very complex. So optical transmission. So what is the second one? Optical generation, right? This is the two main broadening area where optics can contribute, either optical generation or optical transmission. Transmission is definitely for telecommunication application. This generation also somewhere related to the telecommunication or big optical light wave system, the system we implemented here, system we actually showed here. So where you see here, this is the one. Here we could implement an optical system, optical generation, where the optical transmission will happen here. You see, here the optical transmission will happen. Got it, guys? So we will actually discuss about these two separately. That okay, what are the mechanism of optical generation? What are the mechanism of optical transmission in broad? Okay, guys. Okay. So let's see. Uh, any questions so far? I just try to give you some example that where is the scope of using your idea so far you have learned. Right? We are still call it millimeter wave, light wave system or millimeter wave system. We also call it light wave system, which is in millimeter range or millimeter wave. So we have we have came to a understanding that we have two scope of implementation of our light wave system. One is the optical transmission of this millimeter wave and optical generation of this is one, this is two, the optical generation of millimeter wave. Let's see optical transmission first. We will discuss individually two. Optical transmission of a millimeter. How you can transmit your signal through this millimeter. Whenever we say transmission, we actually means an RF signal. How I can transmit an RF signal through optical signal. Okay. So this is a typical example. For example, you have a data signal. Data signal, you modulate the data signal by a carrier or LO reference. For example, you have a very small data signal, few kilohertz, 10 kilohertz, for example. That is we typically do in telecommunication, right? So this carrier reference is LO, for example, which is few gigahertz, like in gigahertz range. Just to modulate it, like low frequency signal. This is the purpose of modulation, right? Whenever we transmit a signal in the telecommunication, we modulate it because of what? We want to increase its energy in the waveform, and which actually means it's a high frequency. So it will have less affected by this noise. That signal will be go to the laser. So if that signal goes to a laser, so is it a DC signal? Probably not, because data signal is nothing but a fluctuating system, 0 1 combination, something like that. So it's actually an AC signal. So in the diode, usually what is the diode input? A constant current. Whenever you give a constant current, you get a constant light as an output. We have seen it in diode mechanism. But now what you're doing, you are actually fluctuating this current. The way you fluctuate is actually the same form of the your signal. That's the same way this light will be fluctuating. Means actually if you can detect in the photo detector this fluctuation, ultimately you can actually detect the data, isn't it? So you see a conventional fiber optics link where we millimeter wave signal is actually transmitted. So that's why actually we say optical transmission of the millimeter wave signal, isn't it? Millimeter wave, which is actually our optical signal. So you are transmitting a signal through this millimeter wave. Probably this is the most simplest the mechanism, but not user friendly. I will let you know why is not user friendly. You see what you are doing, you are actually trying to fluctuate this current in the laser, which will actually ultimately make the diode laser unstable. It's not very suitable. Like the way you change the data here, this one, we are expecting that the same way the light will fluctuate. Light will fluctuate. This is RF and this is light, like optics. This is like general idea. But whenever you fluctuating the input current of this laser, this will not be accordingly nicely, because there is a chance of that this laser current, we have seen it, there is a threshold current is required for laser, right? So if it above or below that threshold, then the light will not be generated properly. This is the most simplest, guys. Are you understanding the concept, guys? Give me some feedback. We will derive in equation, no problem, guys. So let us first understand in the schematic, because equation will be a little bit complex, so I don't want to make you deserted. Okay, so Shamim is there. Is there any I didn't give any notice that some that like, is there a reason that only like you are, or few students are here, Shamim?
Sir, probably the notice came later. Maybe everyone didn't
Because
see
it
it.
was typical time, it's supposed to
Yeah.
be here, right? This time.
Yes, sir. Yes, sir. So also the
So,
network is troubling some today.
oh, network is doubling today.
Also, I've
Okay.
dropped some connection several times.
In Wi-Fi.
Yes, sir.
Okay. So, no problem. When is your exam? Let me stop recording. So when is your exam?